The history of physics and space technologies is a fascinating journey that dates back to the early 20th century. One of the key figures in this history is Robert H. Goddard, often referred to as the father of modern rocketry. In 1926, Goddard successfully launched the world's first liquid-fueled rocket, laying the foundation for future space exploration. Another milestone was the launch of Sputnik 1 by the Soviet Union in 1957, marking the beginning of the space age. This event spurred a space race between the United States and the Soviet Union, leading to significant advancements in physics and technology. As of 2021, there have been over 2,000 satellites launched into space for various purposes, including communication, weather monitoring, and scientific research. The International Space Station ISS, a joint project involving multiple countries, has been continuously inhabited since November 2000, serving as a platform for scientific experiments and international cooperation. The Mars rover missions, such as Curiosity and Perseverance, have expanded our understanding of the Red Planet and paved the way for future human exploration. In terms of numbers, the cost of launching a single satellite into orbit can range from $10 million to over $400 million, depending on its size and complexity. The ISS, with a construction cost of approximately $150 billion, orbits the Earth at an average speed of 28,000 kilometers per hour, completing an orbit every 90 minutes. These figures highlight the significant investments and technological achievements in the field of space physics and technology. Fundamental physics concepts play a crucial role in the development and operation of space technologies. One such concept is Newton's laws of motion, which form the basis for understanding how objects move in space. For example, the first law states that an object will remain at rest or in uniform motion unless acted upon by an external force. This law is essential for spacecraft navigation and trajectory calculations. The second law, which relates the force applied to an object to its acceleration, is fundamental in designing propulsion systems for spacecraft. In space, where there is no air resistance, these laws govern the movement of satellites and spacecraft with incredible precision. Another key concept is Kepler's laws of planetary motion, which describe the orbits of planets and satellites around celestial bodies. These laws are used to calculate the trajectories of spacecraft and ensure they reach their intended destinations. The concept of escape velocity, derived from Newton's laws, is critical for launching spacecraft into orbit and beyond. Escape velocity is the minimum speed required for an object to break free from the gravitational pull of a celestial body, such as Earth. For Earth, the escape velocity is approximately 11.2 kilometers per second, highlighting the immense energy needed to overcome gravity. The principle of conservation of energy is also vital in space technologies. Energy cannot be created or destroyed, only transformed from one form to another. This principle is applied in the design of power systems for spacecraft, such as solar panels and nuclear reactors. In space, where resources are limited, maximizing energy efficiency is essential for long-duration missions. Quantum mechanics, a branch of physics that deals with the behavior of particles at the smallest scales, is increasingly relevant in space technologies. Quantum entanglement, a phenomenon where particles become interconnected regardless of distance, has the potential for secure communication systems in space. The concept of time dilation, predicted by Einstein's theory of relativity, is crucial for satellite navigation systems like GPS. Satellites in orbit experience time dilation due to their speed and proximity to Earth's gravitational field, requiring precise adjustments to ensure accurate positioning. The utilization of fundamental physics concepts in space technologies continues to push the boundaries of human exploration and scientific discovery. From understanding the motion of celestial bodies to harnessing quantum phenomena, physics remains at the forefront of innovation in space exploration. As we look to the future, advancements in physics will drive the development of new propulsion systems, communication technologies, and exploration missions beyond our solar system. Space exploration relies heavily on the principles of physics to overcome the challenges of venturing into the unknown depths of the cosmos. One fascinating application of physics in space exploration is the use of gravitational slingshot maneuvers to propel spacecraft across vast distances. This technique involves utilizing the gravitational pull of planets to increase a spacecraft's speed and change its trajectory. For example, NASA's Voyager 1 and Voyager 2 spacecraft used gravitational assists from Jupiter and Saturn to reach the outer reaches of our solar system. These maneuvers not only conserve fuel, but also enable spacecraft to explore distant regions that would otherwise be unreachable. Another intriguing application of physics in space exploration is the concept of aerobraking, where a spacecraft uses a planet's atmosphere to slow down and adjust its orbit. This technique was successfully employed by the Mars Reconnaissance Orbiter to enter a stable orbit around Mars while minimizing fuel consumption. The precision required for aerobraking maneuvers highlights the intricate interplay between physics and engineering in space missions. In terms of numbers, the Hubble Space Telescope, launched in 1990, has captured over 1.4 million observations and revolutionized our understanding of the universe. The telescope orbits Earth at a speed of about 28,000 kilometers per hour, completing a full orbit every 97 minutes. Its images have provided valuable insights into distant galaxies, black holes, and the expansion of the universe. The James Webb Space Telescope, set to launch in 2021, will be the most powerful space telescope ever built, with a primary mirror spanning 6.5 meters in diameter. Once operational, it is expected to revolutionize our understanding of the early universe and the formation of galaxies. The Mars Curiosity rover, launched in 2011, has traveled over 23 kilometers on the Martian surface and transmitted valuable data back to Earth. Equipped with advanced scientific instruments, the rover has made groundbreaking discoveries, including evidence of past water on Mars. These missions exemplify the innovative applications of physics in space exploration and the remarkable achievements made possible through scientific collaboration and technological advancements. Satellite communication plays a vital role in modern society, enabling global connectivity and information exchange. Physics is at the core of satellite communication systems, from the transmission of signals to the orbiting of satellites. One interesting fact is that geostationary satellites, which orbit the Earth at the same speed as the planet's rotation, appear stationary from the ground. This unique characteristic allows for consistent communication with fixed ground stations. In terms of numbers, there are currently over 2,000 operational satellites in orbit, with a significant portion dedicated to communication purposes. These satellites facilitate a wide range of services, including television broadcasting, internet connectivity, and global positioning systems. The International Telecommunication Union allocates specific frequency bands for satellite communication to prevent interference and ensure efficient signal transmission. The physics of electromagnetic waves is fundamental to satellite communication, as signals are transmitted via radio waves between ground stations and satellites. The Doppler effect, which describes the change in frequency of a wave relative to an observer's motion, is accounted for in satellite communication to maintain signal accuracy. The latency in satellite communication, caused by the time it takes for signals to travel between Earth and satellites in orbit, is a critical consideration for real-time applications. Advances in physics and technology continue to enhance satellite communication capabilities, with the development of high-throughput satellites and laser communication systems on the horizon. Spacecraft propulsion systems are essential for maneuvering and navigating in the vast expanse of space. The physics behind these propulsion systems is fascinating and complex, involving principles of motion, energy, and thermodynamics. One of the most common propulsion systems used in spacecraft is the chemical rocket engine. These engines work on the principle of Newton's third law of motion, which states that for every action there is an equal and opposite reaction. In a rocket engine, fuel is burned to produce hot gases that are expelled at high speeds through a nozzle, generating thrust that propels the spacecraft forward. The Saturn V rocket, used in the Apollo missions to the Moon, remains one of the most powerful rockets ever built. It stood over 110 meters tall and could carry payloads weighing up to 145 metric tons. Another interesting propulsion system is the ion thruster, which uses electric fields to accelerate ions and produce thrust. Ion thrusters are known for their high efficiency and long-duration operation, making them ideal for deep space missions. The Dawn spacecraft, launched in 2007, used ion thrusters to explore the asteroids Vesta and Ceres, covering a total distance of over 5 billion kilometers. Nuclear propulsion systems represent a cutting-edge technology that harnesses the energy released from nuclear reactions to generate thrust. These systems offer the potential for faster travel speeds and extended mission durations in space. The Project Orion concept, proposed in the 1950s, envisioned spacecraft propelled by detonating nuclear bombs behind a massive pusher plate. While this concept was never realized, research into nuclear propulsion continues for future interplanetary missions. In terms of numbers, the Space Launch System, SLS, developed by NASA, is set to become the most powerful rocket ever built, with a payload capacity of up to 95 metric tons to low Earth orbit. The SLS will play a crucial role in NASA's Artemis program, which aims to return humans to the Moon and eventually send astronauts to Mars. The Falcon Heavy rocket, developed by SpaceX, is currently the most powerful operational rocket, capable of lifting over 63 metric tons to low Earth orbit. SpaceX's Starship, a fully reusable spacecraft designed for crewed missions to Mars and beyond, represents a significant advancement in space transportation technology. The physics behind spacecraft propulsion systems continues to drive innovation and exploration in the realm of space travel, pushing the boundaries of human ingenuity and scientific discovery. Space telescopes and observatories have revolutionized our understanding of the universe, providing unprecedented views of distant galaxies, stars, and celestial phenomena. The Hubble Space Telescope, launched in 1990, has captured over 1.4 million observations and transmitted invaluable data back to Earth. Its images have revealed the intricate details of nebulae, supernovae, and other cosmic wonders, expanding our knowledge of the cosmos. The James Webb Space Telescope, set to launch in 2021, boasts a primary mirror spanning 6.5 meters in diameter, making it the most powerful space telescope ever built. Once operational, it is expected to peer deeper into space than ever before, shedding light on the early universe and the formation of galaxies. The Chandra X-ray Observatory, launched in 1999, has provided groundbreaking insights into high-energy phenomena such as black holes and supernova remnants. By detecting X-rays emitted by these celestial objects, Chandra has unveiled the violent and dynamic processes shaping the universe. In terms of numbers, the Hubble Space Telescope orbits Earth at an altitude of approximately 547 kilometers and travels at a speed of 27,000 kilometers per hour, completing an orbit every 97 minutes. Its instruments have made over 15,000 scientific publications possible, contributing to numerous discoveries in astrophysics and cosmology. The Chandra X-ray Observatory, located in a highly elliptical orbit around Earth, reaches a maximum distance of 133,000 kilometers from the planet during its orbit. Its ability to capture X-ray emissions from distant cosmic sources has led to over 4,000 scientific papers and continues to drive advancements in X-ray astronomy. These space telescopes and observatories exemplify the profound impact of physics on our exploration of the universe, pushing the boundaries of human knowledge and inspiring awe and wonder in the mysteries of space. One of the significant challenges in applying physics to space technologies is the harsh environment of space itself. Space is a vacuum, devoid of air and other mediums that are present on Earth. This vacuum poses challenges for thermal management systems on spacecraft, as there is no air to conduct heat away from sensitive equipment. Engineers must design innovative cooling systems using principles of thermodynamics to prevent overheating and ensure the proper functioning of spacecraft components. Another challenge is radiation exposure in space. Cosmic rays and solar radiation can damage electronic systems and affect the health of astronauts. Shielding spacecraft and spacesuits from radiation requires a deep understanding of nuclear physics and material science to provide adequate protection. In terms of numbers, the cost of space missions can be staggering. For example, the Mars Science Laboratory mission, which landed the Curiosity rover on Mars, had a total cost of over $2.5 billion. This figure includes the development, launch, and operation of the spacecraft, as well as the scientific instruments on board. The complexity of space missions also presents challenges in terms of communication. Signals traveling between Earth and spacecraft can experience delays due to the vast distances involved. For instance, signals from the Voyager 1 spacecraft, which is over 22 billion kilometers away from Earth, take over 21 hours to reach mission control. Overcoming these communication delays requires precise timing and synchronization, leveraging principles of signal processing and information theory. Addressing these challenges in applying physics to space technologies requires interdisciplinary collaboration and innovative solutions to push the boundaries of exploration and discovery. The future of physics in space exploration holds exciting prospects and opportunities for groundbreaking discoveries. One area of interest is the development of advanced propulsion systems that could revolutionize interplanetary travel. Concepts such as nuclear thermal propulsion and antimatter propulsion are being explored to enable faster and more efficient missions to distant planets and beyond. These technologies could significantly reduce travel times and open up new possibilities for human exploration of the cosmos. In terms of numbers, the theoretical maximum speed achievable by a spacecraft using antimatter propulsion is estimated to be around 99% of the speed of light, offering the potential for rapid interstellar travel. Another area of focus is the utilization of quantum technologies in space missions. Quantum communication systems could provide secure and instantaneous data transmission between Earth and spacecraft, enhancing the efficiency and reliability of communication networks. Quantum sensors and clocks could also improve navigation accuracy and enable precise measurements of gravitational fields in space. The integration of artificial intelligence and machine learning algorithms in space missions is another exciting frontier. Autonomous spacecraft equipped with AI systems could make real-time decisions, adapt to changing environments, and optimize mission objectives without human intervention. These intelligent systems have the potential to revolutionize space exploration by enhancing efficiency, reducing risks, and enabling new avenues of scientific inquiry. The future of physics and space exploration is filled with promise, as researchers and engineers continue to push the boundaries of technology and innovation to unlock the mysteries of the universe. Collaboration between physics and engineering in space tech is essential for the success of space missions. Physicists provide the theoretical framework and understanding of natural laws that govern the universe, while engineers apply this knowledge to design and build spacecraft and technologies that can withstand the rigors of space. One interesting collaboration is the development of CubeSats, small satellites that have democratized access to space for universities and research institutions. These CubeSats often carry scientific instruments designed by physicists to study phenomena such as Earth's atmosphere and magnetic field. In terms of numbers, over 1,000 CubeSats have been launched into space since the early 2000s, showcasing the impact of interdisciplinary collaboration in space exploration. The close partnership between physicists and engineers continues to drive innovation and push the boundaries of what is possible in the realm of space technology. The collaboration between physicists and engineers in space technology has led to remarkable advancements in our understanding of the universe and the development of innovative spacecraft and instruments. For example, the Mars Curiosity rover, launched in 2011, has traveled over 23 kilometers on the Martian surface, conducting experiments and sending valuable data back to Earth. In terms of numbers, the International Space Station, ISS, orbits the Earth at an average speed of 28,000 kilometers per hour, completing an orbit every 90 minutes. Over 2,000 satellites are currently operational in space, supporting various communication and scientific missions. The James Webb Space Telescope, set to launch in 2021, will have a primary mirror spanning 6.5 meters in diameter, making it the most powerful space telescope ever built. These achievements highlight the importance of interdisciplinary collaboration in pushing the boundaries of space exploration and technology.